Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the glycol and glycals and the glycal derivative. How that what do you mean by the glycals and the glycals derivative? With the help of that suitable example, we have learned these terms in detail yesterday. So let me revise it quickly here. The glycals means what? That Furano's ring, or the what we can call it as a glucose ring, is formed in the glycal, means there is a double bond is introduced over there, and when this double bond and that simple Furano's ring is combined with coupling with together, and there is a formation of the glycal derivatives, because there is a potential allylic that carbon-carbon double bond is introduced over there, and due to that reason the stereochemical glycals and the glycals derivatives are obtained suitably in a high. That type of the thing we have learned over there. Selectively we can remember. If you observe the ring structure of glucose, you will find that there is two forms, alpha form and the beta form, as we know that. If that anomeric anomeric hydroxyl group is written in some that zigzag manner, then you cannot define it. You cannot say definitely whether it is alpha form or the beta form. That is a general way of representing the anomeric hydroxyl group in this fashion. So that is a general trend. But when that anomeric form, whether it is a what we can call it as it act as a donor or the acceptor, depending upon that nature of that anomeric hydroxyl group, you are converting into as a different substitute, replacing that hydroxyl group by other some group, and when it converted into as other some group, maybe as a halide or what we can call it as a trichloroacetamate or thioglycomate, that becomes as a donor, and some other monosaccharide unit, or maybe as a oligosaccharide, that may be as a acceptor. So that type of the donor and acceptor coupling takes place together. There is a glycosylyl bond formation occurred, and we are getting as a different type of the oligosaccharides. So that type of the thing we have seen yesterday. Today what we are going to see over here, because we are talking about the synthesis of glycoside, and here the glycosylyl bromide. How glycosylyl bromide, glycosyl, that is glycosyl bromide, how we can achieve, or what do you mean by the glycosyl bromide? So our halides, generally bromide is frequently used over here, and so that we can get as a meaning. And if you remember here the structure of that. Let us see here. I am representing one of the structure over here. This is a OH, not like this. Let's see, I can draw this like this, OH over here, and now another one OH, and here hydroxyl group, here also has a hydroxyl group, and here OH hydroxyl group. All the hydroxyl group, when that glucose is generally present in the most stable form, which is a chair conformation, and in the chair conformation whatever bulky groups are there, they are prefer to stay at equatorial position. Due to the steric region, they prefer to stay at equatorial position. That you should remember while representing the structure of cyclic structure of. And now this type of the bond indicate that the stereo, whether this is the alpha form or the beta form, we don't know, because we know that alpha or beta anomers, right? Anomers means what? Alpha side means that hydroxy group should be below the plane, similar to this, and if hydroxy group are above the plane, that we can call it as a beta anomer. Let's see that also over here. Suppose you have this structure. Now I am writing this one OH, and other thing remains as it is OH, then hydroxy group here, another hydroxy group here, and this one is a OH, right? So this is called as a beta form, because this is above the plane, and as we know that this, the line we are representing, this is above the plane. And now another alpha form we can write like this. So let me draw the chair conformation of this glycoside we are talking about here. Suppose we have this hydroxy group at below the plane. This is an anomeric carbon atom, as we know that, and this hydroxy group is known as a anomeric hydroxyl group, and other group OH all are lying at equatorial position. So that is this is a beta form, this will be the alpha form of that, alpha and beta form of that glucopyranos, and they are in the chair form. Now why they are in I am representing these in the chair form, because chair form is the most stable than the other conformations, like as a boat conformation, or in a boat conformation in a simple cyclohexane, you might be knowing there is a flagpole interactions are there. Flagpole interaction, they are replacing or that making or internal energy is increased due to the flagpole interaction, and that's why that boat conformation is a less stable as compared to as a chair conformation. In the chair conformation, if you remember, as a simple cyclohexane structure, and that is the most stable one, than the other conformation structure means just by rotating as a or just by flipping. Flipping is another process, that is not the conformer, but here chair, boat, half chair, twist boat, these are the different conformational structures of that cyclic compound 6-membered ring when we are talking about. Now let us see over here. If you observe these structures carefully, so don't, these alpha and the beta, they are the mixture over here, anomers. Anomers means what? They are the diastereomers differing, they are differ at a configuration only at one carbon atom, that type of the diastereomers are known as anomers of each other, and they alpha and beta are the anomers when they are in the ring form. Then we can designate, or we can call it as alpha or beta. Now if you look at here, there are three sides of if you consider as a reactivity of this chair conformation, what do you find? There is one primary, right? One primary hydroxyl groups are there, like this one, CH2OH. That is a one primary hydroxyl groups are present over here. This is a one. Now if you look at, there are how many second one, CHOH, that are the secondary alcohols. There are three secondary alcohol, or the hydroxyl groups are present in this structure, and one which is again is a CHOH, that is a one anomeric structure. This is anomeric hydroxyl groups are present. So these are, if you talk about the reactivity of this, and when suppose acetylation is carried out on this particular reaction, what do you get? Where the acetylation, generally acetylation will be carried out in base as well as in presence of the Lewis acid. And if you carry out the acetylation in a basic condition, generally as a sodium acetate, the rate of reaction, rate of acetylation will be slower. Whereas if you use these reactions, same reaction, if you carried out in presence of Lewis acid, the rate of acetylation will be increased. So that is the thing you have to remember. For acetylation, we can use, or what we can call it, for the protection of this hydroxyl group, for the protection, and as we know that protection is done in such a way that, or that group is blocked or masked particular functional group, and it can be high yielding product. So that are the thing you have to remember while protecting such a type of the group. And whenever require, we can remove easily at a mild condition, or the protecting group should be stable at the other reaction condition. So these are the some of the criteria for protection, as we already know while studying as a protection and the deprotection over here. And generally here acetic anhydride in presence, suppose as a ACOAC, that is a acetic anhydride in presence of sodium acetate, or we can use acetylation, you can carry it out in presence of the Lewis acid. So here the rate of acetylation reaction is slow, and here is what we can call it as a fast. Rate of acetylation reaction will be fast, and by using this we can carry out. What do you get over here? If you use here the acetylation AC2 in presence of H plus, means this is a Lewis acid. Lewis acid, what do you get? The primary alcohol which is free here, which is more reactive toward the acetylation, and therefore you are going to get first one. This is a compound which you are going to get over here. OAC acetylation takes place here. Another hydroxyl group we can represent, they are lying as it is, and we don't know here this bond indicate that we are not assigning, we don't know whether that hydroxyl group is above the plane or below the plane. If it is above the plane, that will be represented by alpha anomer, and if it is present below the plane, if it is present above the plane, then we can represent by beta, and if hydroxyl group is below the plane, that is called as a alpha side or alpha anomer we can call it. And now if you at an equilibrium, if you go on using in a excess amount of the acetic anhydride, what do you get? What do you get? What do you get, or what will you get over here? You will get here this type of the compound, this one. So here this OAC, all groups get acetylation over there, OAC. Then here you can write ACO, and here also OAC. Means all the hydroxyl group get protected over there. So I am trying to explain the glycosyl bromide undergoes many reaction, as we know that. And here when this nucleophilic substitution can be carried out to make thioglycosides or azidoglycosides, Ag plus and Ag second halophiles are often used to speed up the removal of Br, especially with proper nucleophiles. For example, in disaccharide synthesis, ROH, the other sugar is a weak nucleophile, and therefore acetate, that acetate, just now I already told you that acetate, that ACOH in place of H plus or Lewis acid, nucleophile, good leaving group, and so that we will get as a this one. Suppose now we have got all the groups are protected or oscillation, that is I am going to show over here how that glycosyl bromide is achieved. First one, we carry out this reaction in presence of the Lewis acid. First, this primary alcohol get acetylated, and further in many steps, so that will be converted in excess amount of the acetic anhydride in presence of the Lewis acid. All the hydroxyl group including anomeric hydroxyl group also get acylated, and we will get as a this type of the compound over there. And now here let's see here what do you get here, OAC, then OAC, here also OAC, then OAC, here OAC, acetyl group all are. And when at an equilibrium, when it is treated with hydrogen bromide, right, this HBr, hydrogen bromide, at an equilibrium, what is going to happen, anomeric carbon atom is a very labile to react in an acidic position, so that the acetyl group get replaced by halide, and we are getting as a glycosyl bromide over there. And that glycosyl bromide is this is a structure of glycosyl bromide. Let us see over here. And generally this Br is present at beta position, so that is a Br, and other thing remains as it is OAC, here also as a OAC, here also OAC, and other OAC, this type of the, and this is known as a glycosyl bromide. This is known as a glycosyl bromide. This is a structure we obtain over there, and this nucleophilic substitution can be carried out to make this type of the reaction over there. And now alpha anomer only due to equilibrium such that thermodynamic stability overrides neighboring group participation if F minus and Cl minus introduce CX bond strength increase and equilibrium is slowed. So C beta anomer. Beta anomer also possible in presence of, suppose we have this type of the compound over there. So this glycosylyl bromide we have got, that this one is a alpha anomers. Alpha anomer we are getting here, alpha anomers of this, because beta present below the plane. And when also, if or also when this at an equilibrium, if I am going to see over here, other thing we can write ASC, then here ACO, then here ACO, another one OAC, and here Br at an equilibrium in presence of this one Bu4N Br, then this Br minus is going to attack on this side and this is depart, so that you may get over here this type of the beta anomer. We can easily convert into as a beta anomer. Other group, they are lying at an equilibrium position, and this is a beta anomer of that glycosyl bromide. So alpha, how we are getting as alpha, how we are getting as a beta, that you have to remember over here. So from alpha we can easily made as a beta over here. And now, and once you get as a glycosylyl bromide, and many of the reaction can be carried out with this compound, and so that we will get as a different type of the reaction over here. Suppose we have, let us see, suppose we have a beta anomer over here. Let's see how it can work over here. So let's see that one also. Now suppose as a beta anomer is there. Let's see, I am showing only representing. So my intention to show only as a this acetyl group and this bromide over here. And now here the bromide means this can be, this group can be attacked over there, Br get eliminated, so that other thing remains as it is. I am representing this one, so that you will get another structure like this. Here oxygen, here also oxygen, and then there will be a, what we will get here, positive charge, right? Positive charge, and other things remains as it is. And now when that as we know that beta anomer get reacted with that acetyl, they can form as this type of the ring, and now it will be treated with methanol. Methanol is going to attack at this position at the carbocation, because that carbocation are well stabilized due to the presence of lone pair present on oxygen atom, and therefore you are going to get the product over here, this one. So you may get here O, this protected OMe, this other part we can write as it is. So that type of the compound you may get over there, or this step moves cyclization easier, or that occur when bromide is there. Then reductive elimination makes the glycol, and yesterday we have seen as a glycan also. Suppose as a reductive, and suppose we have a glycosyl bromide, as we know that at alpha position, or maybe for beta position alpha. Let us see a glycosyl bromide, and by using the glycosyl bromide, how we can get, so as we know that Br is over here, then OAC, then OAC, here also is OAC, and next one also as OAC. This is nothing but as a glycosyl bromide, and when this glycosyl bromide treated with the reducing reagent like as a zinc dust, as we know that it can attack or it can be zinc oxide. And now let me show this one properly, oxygen atom over there, then C double bond O, then this acetyl group. Now this Zn attacking obstruct that bromine form as a double bond over there, and this is there, and this way this get eliminated, so that you are going to get the compound over here, this one, then double bond and this compound, right? And now OAC, and other is OAC. This is nothing but as a, what is that? Glycol, right? Glycol. Yesterday we have seen this glycol is a very important one. When it treated with that other monosaccharide unit, they get combined over there, and the electrophile over there. So in this way, yesterday we have seen glycol and glycol derivatives. By using as this glycol and other monosaccharide unit, we can get as a oligosaccharides. So in this manner, how this glycoside is a very important as far as, again, free radical reaction also occur when this is there is a formation of that carbon-carbon double bond, because this one, just like as a zinc dust, as we know that it's a reducing reagent, and we bring the double bond over there, and this type of the derivative is known as a glycol and its glycol derivative that we have discussed yesterday about that thing. So that is a reductive elimination makes the glycol. So this one, nucleophilic addition, this is used to capture the open chain aldehyde, useful for forming carbon-carbon at anomeric center, that is lengthening. Then diethiols also prepared over there. Diethiols are what we can call it as a here as a one more reaction for glycosyl bromide. Here remember how we can use that glycosyl bromide in the different manner. Let us see, suppose as this glycosyl bromide over here, this one, as we know that this bromine, then OAC, here OAC, then OAC, here we can write OAC. When it is treated with, as we know that Bu3SNH in presence of AiBN, azoisobutyl nitride. In a photochemistry we are using this type of the, and tributyl tin hydride, which will act as a, what is going to happen, AiBZ, there is a free radical, and that free radical generated over there, Bu3SN, free radical can combine with this, and there will be a free radical generated, and you are going to get over here, this is the structure which we are going to get here, free radical, then there is a oxygen atom, and other group, they are remains as it is, here OAC, and here also as a OAC, and here OAC. Now this free radical can take as a hydrogen from again as a HSN Bu3 in this fashion, and we can what we can call it as a deoxygenate, this one, or other way, what you are going to get over here you are going to get this one. This is a derivative which you will get over here, OAC, then OAC, so OAC. This is, or if you treat this compound with this one, suppose as a double bond CN, that type. So what is going to happen? This is going to abstract the proton over here. No, the new carbon-carbon bond is formed here. New carbon-carbon bond is formed, and as the new carbon-carbon bond is formed, that is very important as far as a synthetic organic chemistry point of view is concerned, so that you will get here this type of the compound joined over there. So maybe as a this one, then here Cn, and this can abstract the proton from here. That's type of the compound. Derivative you may get over here, then OAC and OAC. This I can abstract the proton from SN Bu3 like this, and you will end up with the compound like this one. So here is we don't know this one Cn. Okay, this because whether is above or below stereochemistry we cannot assign it. OAC, then OAC over here, OAC, and here also as a OAC. These are the different reaction or thioacetal formation for lengthening that compound. So let us see how the reactions are taking place, how that glycosylyl bromides are useful in getting different type of the oligosaccharides. So let us see another what we can call it as a diethioacetals. So how diethioacetals can be obtained? Let us see here. Suppose we have this one. Let us see OH, then HO, then OH, and at anomeric carbon atom, that is hydroxyl group, we can show over here. Suppose is carried out in presence of EH. So this get protonated first, and you are going to get this type of the structure here, H positive charge over there. Suppose this one OH, other OH we can show as it is this one, and now this is a lone pair, they can form as a bond and ring get open like this, so that you will be getting here this one is a OH, and here maybe as a OH, then hydroxy, here OH, then OH, then double bond O, or here H maybe as a positive charge, and then ETSH, that thiol is going to attack over there, and what do you get? You are going to get over here. So here thiol get attack on this carbon atom, and you may end up with the compound like this. This is a hydroxy group, we can show as it is there, hydroxy group, then HO, then here OH, and you can write here yes ET, and that proton comes here, that becomes as a OH2 positive charge over there, and then yes HET, ethyl is going to attack over there, and that get eliminated. So you will get this one OH, then OH, hydroxy group over here, then one hydroxy group here, OH, and there you can write SET and SET. That is a compound which we will get, that is a diethiol. So in this way, so we have seen some of the synthesis of glycoside. In the tomorrow we will see. Today we have seen glycosylyl bromide, how it is useful, what type of the derivatives it can produce, that we have seen. So tomorrow we will see start as a thioglycosides. I think with this let us stop today here. Thank you. Have a nice day.